Hey, and welcome back to Epistem. Today we're doing an episode on phase change materials. So, what a phase change material is it's a material that releases energy during a phase change. So, you can do a lot with that, as we'll find out. We do a lot of subjects in material science, and specifically this thing feels very sci-fi to me. I think this is one of the cooler subjects that we've talked on. So, with this study, with this paper, what the researchers were studying was how you can optimize these phase change materials for their use in different technologies. So there's been a lot of research done in the past about phase change materials, and they've been the subject of a lot of lab work, but they're looking at how can we optimize these for use in industry. How can we make these usable in a lot of different ways? So we go ahead and jump right into it. I'm Luke.
And I'm Hunter. And you're listening to Epistem, a show where we explore papers in STEM fields and let you know what they're all about. So as Luke said, we're talking about phase change materials today. So for those who don't know, a good example of a phase change material that's very common is water. Water and ice between solid and liquid. It's a phase change material and has been used for insulation purposes and cooling purposes for millennia now. Cooling methods that utilize water have been dated back to 2,000 years ago. These systems are now being optimized and actually being used for thermal energy storage, thermal transfer, energy conversion, and other utilizations such as drug release systems, thermotherapy, and thermal protection, as all stated within the abstract of this paper.
Yeah, there's a lot you can do with it. The first thing you should really understand about these materials is that they have a limit to how much energy they can store. So naturally, that amount of energy, it's called the latent heat. It is the amount of energy it takes to change the phase of the material, or how much energy goes into that phase change. And there's different types of phase changes, as you may know. Think about the water example. There's solid to liquid, liquid to gas. There's even, maybe not for water as often, but solid to gas is also one. Solid to liquid phase changes are the ones that are most widely used within the world of phase change material technology. So the way that you typically prepare one of these pieces of technology is by filling a porous material with the phase change material, or a PCM. You can use carbon nanotubes, which have a lot of useful properties. There are plastics that are porous. You can use metal organic frameworks. Yep, we're bringing metal organic frameworks back into it. There's a lot of different properties that you can tune for. And again, we'll see those later when we start talking about some of the applications.
As Luke said, the most commonly used is either solid to solid or solid to liquid or vice versa, PCMs. And there's a reason behind that. So let's say we're using a liquid to gas or solid to gas. That would require a system to have a lot more capacity, a lot more space, because a gas is very high pressure and takes up a lot of space. So that usually isn't utilized in a system because it would just require larger area and just a larger capacity in general, compared to the solid to liquid, which are more comparable space-wise.
Yeah. A lot of the time, some of the decisions that you make for what you're going to use or how you want to use it comes down to the size of the pores for the structure of the PCM. For very small pores, you have to use things like what's called vacuum impregnation, which I know is a pretty vulgar term, but it basically is just a way to pull these PCMs into the material. Yeah, yeah, it's not the most pleasant term, but vacuum impregnation. Get it in your head.
Let it impregnate your head.
Some applications. Yeah. Some applications for these include smart materials. You can use them in fingerprint recognition. It's used a lot in drug delivery. We actually touched on that in our episode, Drowning on Air. We talked about metal organic frameworks being used for water extraction. It can be used for stealth technology, which we hinted on in that episode, I believe. And it can be used for energy conversion, which is a pretty hot topic right now.
So, as we've talked about, this paper is primarily based on the optimization of PCMs and also utilizing them for energy storage, hopefully for sustainable energies. And a way that they're doing that now is to use composite PCMs, which is mixing pure PCMs with composite materials. There's a wide variety of different materials that are being tested right now, but it essentially mixing these materials allows for the PCMs to absorb more energy and be able to store it easier.
Exactly. Yeah, a lot of the times when we're talking about tuning these things or making them for specific applications, it really all comes down to making small changes on pretty much the molecular level that have wildly different effects on the macro characteristics of the material. So first, I want to talk about optimizing these things for thermal conductance. So if you want a material to conduct heat evenly, like maybe a heat sink, or if you're using it as a component in a gauge, some kind of temperature gauge or electronic component. In the past, what would be done is that you would add a lot of filler material or additives to enhance the properties of the material as a whole. That's fine for most materials in most applications, but more additives also means that there's less energy available from the phase change. So that kind of defeats the purpose of the phase change material. They found that the best structures for optimizing thermal conductance and for achieving these goals would be to use continuous structures. So something like a foam or carbon nanotubes, something that's larger than little grains or little tiny pieces mixed in throughout. And it really comes down to surface area. That's kind of the key component of this. The more interaction between the face of the additives and the phase change material, that's more thermal resistance. So at these meeting points between the additives and the host material, the more of that there is, the more difficult it'll be, the more resistant it'll be to change temperature and for energy to pass through it and to fill it up. So what we find a lot of times, we've said this before, is that surface area is really a big component of a lot of these material properties. So I want to take a moment also and talk about energy conversion. So this is kind of, like I said, a hot topic because especially now, as we move more towards green energy, there is the concern of if you're talking about wind energy, there's more wind available at night. If you're talking about solar energy, there's obviously more sun available during the day. Does that mean you can only have energy for certain hours of the day? That's obviously not ideal, and I don't think that would fly for most people. So being able to store energy is pretty important. For solar energy, it would store energy from the sun in the form of latent heat within itself. So alone, PCMs don't really absorb photons or solar radiation particularly well, but with additives they can. And again, we're kind of seeing the whole interaction between adding additives but not defeating the purpose of it being a phase change material, not taking away too much of its latent heat. So they add things to the PCMs that will enable it to absorb photons better, like carbon materials or dyes. If something's black, it absorbs more thermal energy from the sun. And just various metals, really. So you can add these things in to increase its ability to absorb sunlight. One of the issues that they run into with this application is that it takes a long time for it to quote-unquote thermally charge, so to really reach that full energy capacity. But what they can do is tune it by distributing these optical absorbers, so to speak, into the PCM. So let's say you had a pot of soil and you wanted to pour some water into the pot and wet the soil in the whole pot. So all of the soil is wet. It would be kind of time consuming if you just poured all the water on top. I mean, I guess it wouldn't be that time consuming, but it would take some time for that water to seep down through the soil and reach the bottom and get all of the soil wet. So you can make this faster if you put a bunch of straws in the soil, because then the water would have a way of kind of filling out the whole pot rapidly. And that's kind of what these things are doing, these optical absorbers. What they're doing is you fill the phase change material with them, and then they're little hot spots where sunlight can really easily be converted from optical to thermal energy, or from radiation to thermal energy, I guess would be the proper way to say that. And it turns out this is very efficient. It enables rapid thermal charging, and the whole process of converting solar energy to thermal energy is very efficient. It's over 90% efficient. So it's a pretty well thought out process and well fleshed out. But that's not the only conversion that you can do. So that's solar, light energy to thermal energy. You can also, it's not quite as efficient, but you can convert electric energy to thermal energy as well. And the way this works is you would put a PCM into a conductive supporting material like carbon nanotubes or graphene, or just a electrically conductive metal organic framework. And at a certain voltage, a phase change will occur. So this is, like I said, isn't quite as efficient, but it is possible. And what's interesting is you can also convert magnetic energy to thermal energy. And this is cool because it's basically a brand new field of research. The researchers talk about in the paper how some of the implications are interesting and how they would like to do it. It's possible. It's even less efficient than the electric to thermal conversion, but it's a wide open door that just hasn't been explored yet. So pretty cool that that's out there and that they mentioned that.
Based on what Luke just said, essentially right now, sustainable energies, whether it be solar, whether it be magnetic or electrical to thermal conversions, they are very good at collecting that energy, but it's hard to sustainably hold that energy and keep it contained because, as is with the sun, during the day we get the most supply of energy from the sun. However, the highest demand for energy is at night. So there has to be a good way to control that heat and keep it contained so that it can the energy can stay for longer than we're using it right now, and we're able to actually control that energy better. And that is where the PCMs come into place.
Do you want to take a quick break?
Let's do it. So welcome back to the show. Now Luke is actually going to bring up some really interesting topics relating the PCMs to maybe science fiction, possibly those Star Trek, Star Wars fans out there. Better listen up.
Yeah, so this is really the crazy stuff. It sounds like science fiction, but I mean this is real stuff, real technology. So let's see. There's this is actually something that the researchers in this paper did. They did a lot of analyzing other methods and other uses in the paper. I guess that's pretty common with a lot of research, but this experiment they did themselves. So they used these phase change materials to generate a fluorescence emission material. So this is really cool. It was composed of 3 parts: the metal organic framework, which is the structure for the whole material. There are also inside of it things called carbon quantum dots, and these are the luminescent component. So they're basically it's a material that emits light when it absorbs energy, which is really cool. I might have to talk more about those in the Curiosities episode. And then the third component is the PCM, which is stearic acid, and that stores the thermal energy. So the MOF kind of holds all these components together. So basically what happens is whenever this PCM releases energy, it causes these carbon quantum dots, or CQDs, to illuminate a red, green, and blue multicolored fluorescence, which is stable for a very long time. And there are applications for this, possibly in LEDs or for sensors. But really, I just think it's cool. That's why I talked about it. I just thought that was kind of neat that you can have this material that just glows based off the energy inside of it, which is, I don't know, it's a cool idea.
Yeah, and as we talked about earlier in the episode, this paper is not totally based on sustainable energies and whatnot, as Luke just forementioned. But another way that PCMs are possibly going to be used in the future and are being trialed for right now is thermotherapy. So there's a lot of people out there that have allergies, whether it be hay fever, whether it be just general allergies throughout the year. But people get nasal congestion and nasal itching, and just it's just really annoying to have. Currently, in our modern age, everybody is wearing masks almost everywhere right now. So what I'm about to talk about doesn't seem that far out. So researchers have been looking into using PCMs for thermal energy harvesting within masks. So essentially creating a sponge-like material inside of a mask for an air filtration purpose, so that less pollen and less just irritants can get into a mask and actually help prevent you from getting nasal congestion and just other allergic reactions as you normally would. So for those that are going to be continuing wearing a mask in the spring, which is most likely all of you, you should look into this. There's possibly going to be some products out there that are using PCMs to help your allergies.
Yeah, absolutely. It's definitely a lot better to have just an optimized material than have a big, chunky filter on the side of your mask. I would imagine that would be pretty appealing. But I want to talk more about thermotherapy because there's an interesting addition they made to that mask as well, or to a mask as well. So you can have a PCM filtering or purifying your air as you're breathing it. But it's also kind of cool because some of the ways to treat allergies that are out there. There's obviously medicine, which comes with its own complications and side effects. But you can also treat it by inhaling hot air for a period of time. This is kind of a pretty simple, clean way to treat allergies. This is something that you have to do repeatedly, but at least there's no medication involved. It's just hot air, about 40 degrees Celsius. Inhaling it into your nose for a period will help clear up your sinuses. So they can actually charge a PCM with energy and integrate it into a mask such that you're inhaling the energy that it's releasing, the thermal energy anyways, in the air. And you're inhaling hot air through your face mask, which is serving the purpose of thermotherapy and making your allergies better. So it's cool because it can be a preventative thing, it can be a treatment, it could be both. And like we said already, it's just something that's on your face and it's not super obtrusive. Pretty cool application there, in my opinion.
Well, running along with that idea, PCMs have actually been trialed and are talked about in this paper for drug release systems. So due to PCMs having their change materials, being able to change a lot and fluctuate their substance with changes in temperature, possible uses of capsules being surrounded by PCMs, allowing for slow drug release in a body because the phase change material, whatever it might be used, they're looking into a lot of different kinds of PCMs right now. But researchers are looking into specific PCMs that allow for drug release to be as slow or as fast as prescribed or as wanted. So then someone could just possibly in the future, not sure how far out, but possibly in the future, just take a drug and it slowly releases into their system. So then they could just take one pill rather than one a day for a week.
That's really cool. So now I'm going to shift the discussion a little bit and talk about something that I hinted at, I don't even know, ages ago. If I can find the audio, I'll play it now. Potential for it. And I know I mentioned something about using this technology for stealth, but you're just going to have to stay tuned if you want to hear more about that, because it is going to be involved with another research paper that's coming up in a few weeks. So yeah, I mentioned how there was an application for MOFs and in this paper PCMs as well in infrared stealth technology, which is just wild. So basically the way this works is infrared stealth is talking about thermal cameras. So thermal cameras they don't detect the temperature of something necessarily. They only detect temperatures that are different than their surroundings. So if something is going to be thermally invisible, it needs to be the same temperature as its surroundings, as the background. So what they do to achieve this is they have something that's already been developed, a Kevlar nanofiber aerogel film, KNA film, as it's referred to. One of these things is fabricated. It's a very thin, flexible, and highly porous material that acts as a good thermal insulator. So because it's porous, that means you can fill it with PCMs. So they put PCMs in and into this film and cover it with a hydrophobic coating. So basically what you have is this material film around, like a car or a jet or something like that. And it's you got this coat that absorbs infrared and stores it as energy. So that you're basically thermally identical to your surroundings. It's almost like you're exhausting no heat, which is really cool and has a lot of interesting stealth applications. So you might think, oh, that doesn't sound good. You're just going to trap all that heat inside. Is that not going to make it? Is that not going to make it overheat inside of that coat? And no, it's not, because that heat isn't staying in the form of thermal energy. It's being stored in the phase change. That's the whole idea of the phase change materials. It's not like something's continuously heating up. It's just converting that heat into this latent energy inherent in the phase of the material. So it's a really cool application there. No heat gets out from whatever you're coating in this KNA film filled with PCMs, and that's all there is to it, really. I mean, I say it like it's simple, but it's definitely not. Definitely some advanced materials going on here. But if this is the stuff that they're publishing, it makes you wonder what else is out there as far as stealth technology goes.
Yeah, really interesting stuff. I bet there's a lot that we don't know about PCMs and a lot that we don't know about the stealth technology. That's possible.
Oh, for sure, yeah. I mean, there's a lot that we didn't even touch on in this paper. There's a lot in here, and this is just one paper, one study.
Yeah, as usual, we'll have a link to the paper so that you can check this paper out yourself if you want to. And also we would like everybody to continue on their own personal research. If you find PCMs or any other material that we look over interesting, give us an email and we can actually put you with some sources and some other information about the topics that you find interesting.
Yeah, absolutely. I know. I think materials are real cool. I find them pretty interesting. I'm always psyched to do papers like this. But on that note, the name of the paper is, if you want to look for it on your own, or if you don't feel like finding the link, the name of the paper is "Optimization Strategies of Composite Phase Change Materials for Thermal Energy Storage, Transfer, Conversion, and Utilization." Some of the researchers working on this paper are Zhao Chen, Hongyi Gao, Zhaodi Tang, Wenjun Dong, Ang Li, and Ji Wang. This paper was published in the Energy and Environmental Science Journal on the 26th of September of 2020. If you got any questions, feel free to hit us up on our email. It's epistem.pod@gmail.com.
And also, check us out on Instagram. Our Instagram is epi.stem.
Stay tuned, because here pretty soon, probably within the next week, you can find us on YouTube. It'll just be, for now, the audio recordings of the episodes. But we'd like to maybe do something with that in the future, so maybe give us a sub on YouTube. You'll be one of our first subscribers.
And as usual, if you're feeling really generous, hit us up on patreon.com/epistem.
Yeah, thanks for listening.